Chemistry time! Today's bell work says, explain how gases behave when the temperature changes based on your laboratory data. Hannah, what did your laboratory data show you about the volume and temperature of a gas?
When the temperature decreased, the volume also decreased.
Right, when the temperature went down, the volume also went down. And we call that kind of proportionality
Directly proportional.
directly proportional. So, if this is true, what would happen if the temperature increased to the volume of the gas?
The volume would also increase.
The volume would also increase. Good. So can you think of an example for that? What should we do to make our balloon get bigger by increasing the temperature?
We have to heat it up.
Heat it up somehow. Like when I was 6 years old, I had a balloon, and we parked in the Walmart parking lot, and the balloon was in like the back part of the back seat, and like underneath the rear windshield, the rear windshield. And when we came back, the balloon had popped. So that's because the volume increased too much. So today we're talking about gas laws. The first of which is given by this thing that Hannah just said. Very good, thank you. Given by this thing Hannah just said, which is that temperature and volume are directly proportional. So the first gas law we're going to talk about is Charles's law. Charles' law. So some people say Charles's, some people say Charles. Depending on which way you want to say it, Charles's you would write Charles apostrophe S. Charles you just write Charles S apostrophe, well, Charles instant S, so just Charles apostrophe law. Anyway, all of that aside, Charles' law is given by the equation V1 over T1 equals V2 over T2. One little aside that we have to say before we continue is that for these to work correctly, it doesn't matter what units volume and pressure are in as long as they are the same for before and after. But temperature must be in kelvins. Temperature, so let's just write this in our little aside box here. Temperature, yeah, like in your margins or something, I don't know. Temperature must be in Kelvin. Why? What doesn't the Kelvin scale have?
Negative.
It doesn't have negative numbers. And since it doesn't have negative numbers, we can comfortably divide with it, right? If we try to divide by negative, we get a negative volume here. And that doesn't exist. There's no such thing as a negative volume. So, temperature must be in kelvins. Are we generally, do you think, trying to find the quantity of volume 2 divided by temperature 2? Like, is this what we want to find?
Probably not.
Probably not. Probably we want to find one or the other of one of these four. So we're going to have to manipulate this somehow, which you already know how to do. So this is how we relate volume and temperature. Once again, you can see from the equation, if the temperature goes up here, the volume has to go up too for them to be equal. So for instance, if we just had something like 1 over 1 equals 2 over x, well, of course the x would have to be 2 also for them to stay equal.
Right.
Right. This is just without units, but you can see how the proportionality works. Moving on. The next type of gas law we need to talk about is called Boyles Law. And I remember these by the fact that the word boil is like, like boiling water, like it has to do with temperature, but Boyles Law does not have to do with temperature. So Charles' law is the one that does deal with temperature, Boyles' law does not. Boyles' law is just pressure and volume. Pressure 1 times volume 1 equals pressure 2 times volume 2. So in the previous example, in Charles' law, we had volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. And we said that they were what kind of proportional? Directly proportional. And in this one we have multiplication instead of division. So what would you guess kind of proportionality this would be?
Indirect.
These are almost inversely proportional.
Inverse.
Inversely proportional. So if our pressure increased on a gas, what would its volume do?
Decrease.
So pressure goes up, volume goes down, and vice versa. And vice versa. Once again, pressure and volume can be given in any units as long as pressure 1 and pressure 2 are in the same units and volume 1 and volume 2 are in the same units. So things like, we could have gallons of gas as long as the gallons stay the same afterward. We could have millimeters of mercury or bars or torricellis, anything, pressure, as long as it's the same P1 and P2. Good?
Yep.
Okay, and the last of the single gas laws is called Guy-Lussac's law. I heard this pronounced when I was in chemistry as Guy-Lussac. The real French pronunciation would be Gay-Lussac. And we just don't like to say that word very much in America. I guess we don't
Is
want
it,
to.
what did you say it was, French?
French, yep. The
I
United
like that.
States French. You like the French version, right? And that's fine. Guy-Lussac's law relates pressure and temperature. I think this is one of the most interesting ones, or one of the three. I think this is the most interesting one. You can't say things like one of the most interesting ones when there's only three of them. This is the most interesting one, and I just like the examples of it. So this one relates pressure and temperature. Once again, they're division, so we can tell that they're going to be what kind of proportional? Directly proportional. Therefore, if pressure goes up, what is the temperature going to do?
It also goes up.
Temperature goes up. You've experienced this before. In fact, this process here, this exact one, pressure going up and therefore temperature going up, is called adiabatic heating. And this is what causes the like space shuttle or a satellite coming in from orbit to get really, really hot. People have a misconception where they think that, so here's your satellite. I'm going to draw a little Gemini capsule here. People have a misconception that it's friction, and it just gets so hot from the friction, but that's not actually true. That's part of it, certainly. There is obviously a lot of friction. But the main thing is that in front of the space shuttle here, the space capsule here, in front of the space capsule, the air is being pressed so much because basically this is crashing into them at a really, really high velocity, and they don't have time to scooch out of the way like they do when I just move my hands through the air. And so the air gets squish, 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 and the more squish the air gets, the more it heats up. You can also recognize this, like if you ever used a bicycle pump,
Oh, yes.
that gets hot. And you might have even thought that was just from friction, but it's not. It's something called adiabatic heating. And there's the reverse, which is called adiabatic cooling. Can you think of an example of adiabatic cooling, where pressure decreases?
Oh, yeah, when you turn your aerosol can.
Yeah, exactly. This is why they say don't use the spray air or hairspray or anything aerosol can upside down, because if you do, first of all, the upside down doesn't really matter for this, but here's your upside down spray container. As the pressure gets released, because you're spraying it, pressure is going down, the temperature must also go down. It gets really quite cold. If you ever hold down a spray paint can or hairspray or canned air, it gets really quite cold. Especially with canned air, it gets cold enough that the air can liquefy. And the reason they say don't hold it upside down is because the liquid runs to the bottom and you end up spraying out liquid air, which is extremely cold, and you can burn yourself. Well, you can frostbite yourself. Questions about Guy-Lussac's law real quick?
Nope.
Nope. Okay, so once again, as long as the pressure and the temperature, as long as the pressure is in the same unit, you can use whatever pressure unit you want. But temperature must be in.
What were we saying?
Temperature must be in what unit?
Kelvin.
Kelvin. These are all great. We love to talk about them, but the one we mostly use, in fact, is easier, and this is the one I would memorize if I were you. This is called the combined gas law. And it is just P1V1 over T1 equals P2V2 over T2. And with this, you can manipulate them any way you want to get the answer that you need. Make sure your temperature is in kelvins. Make sure your pressure is in the same unit from 1 to 2. And make sure your volume is in the same unit from 1 to 2. This is the one I would memorize, and this is the one you can use to solve all of the problems that deal with any of these.
It's directly proportional?
Yeah. If you have questions, and you let me know, if you have questions, leave them in the comments. Bye! Oh, I have to switch to the thing first.